The generalized pigeonhole principle extends the simpler case where you simply have more pigeons than you have pigeonholes to put them in. So at least one pigeonhole has to have two things in it. This extends it to a more general case. We will be using the ceiling function in this one here. So I've got that notation in the statement. Here's what it says. If you're going to place n objects in m boxes, then there is a box with at least the ceiling function of n over m. In other words, if you take n objects and you're going to put them in m boxes, you can divide n by m to calculate how you would most evenly put objects in the boxes. If you have a fractional part left over, you're going to have to go one more than that, and that's what happens with the ceiling function. You have to round up to the next one because some box has to contain that many. So I'll give a quick sketch of a proof, and it's actually a proof by contradiction. If for some integer k less than n over m, all m boxes have at most k objects, then the boxes contain how many objects? Just a matter of figuring out. You have m boxes, and you have no more than k in each, so they contain at most m times k. But look at what we assumed here. M times k is less than n, so not all objects are accounted for in the boxes. So that can't be. This can't be. Thus, k must be greater than or equal to m. That is, some box has at least n over m, and it's the integer bigger than or equal to it, objects. It's really fairly natural, and I think in some of the examples you see why this is not strange. Let's see. Suppose we have 20 buses seating at most 50 each, and they carry 621 passengers to a ball game. So then some bus must have how many passengers? Well, we'll try to divide them up equally, right? We'll take, this is the number total passengers. This is the number of boxes we're going to put them in, so to speak. So we're going to take n over m, which is 621 divided by 20, and I'm pretty sure that's 31. And with the remainder of 1 plus remainder of 1, like so. So that says that we need 31 buses, but that's not enough. If we put 31 in each bus, then some bus must have one more put in it. There must be a bus with at least 32. So in fact, the greatest integer, or sorry, the ceiling function of 621 over 20 is equal to 32 because this is bigger than 31. After a passenger train is disabled, buses are called in to transport the passengers. Each bus can hold 36 passengers, and there are a total of 413 passengers. So in this case, we don't know how many buses. That's a little different, but it's pretty much the same idea, right? So you know that the buses can hold 36 each, and there are 413 passengers. So if you stuff them each with 36, how many buses do you need? Well, it's the same idea. 413 divided by 36 is equal to, and then I'll do a little quick calculation on this, and you can do the same and figure out what is 413 divided by 36 and see that it's 11.47 and some. 2 continuing. So 12 buses are needed. And if I ask you a question like that and you say that, you give me this answer here, I'll say no, it's this. Yes. Right? You can't have a fractional part of a bus. Now, if we go back to the first example that we were doing in this pigeonhole idea, namely the one where we had the 6 different colors of balls in a box. So there were 6 colors. So how many would we have to draw from the box to be sure that we got at least 4 of the same color, whatever color it is, I don't care. At least 4 of some color. How many would we have to draw from the box to be sure of doing that? Well, let's see. Would we have to draw 4 times 6, 24? Actually, I don't think so, right? Because what we can do is say, well, let's find out how we can fill them all with 1 fewer. So 4 minus 1 times 6 is 3 times 6 equals 18. That would be 3 in each, evenly done. And so 1 more, so 18 plus 1 equals 19, would force at least 4 of the same color. Okay, you see what I did there? I took 1 less than that times 6, the number of colors, and added 1. Okay? All right. Now this is a little more interesting, and so I'm going to stop this here. I have 2 fairly interesting ones we'll do on the 3rd video.